Good morning. Dzień dobry. It's wonderful to be in Poland. This is my first time here. And I'm very excited to be talking about functional principles today. How many people have done any functional programming? Ooh, a lot. Wow. Wow. Okay. Some of this you guys will already know then, but that's okay because I'm not going to talk about functional programming today, except that I'm going to talk about it a lot. But what I'm not going to do is teach you how to do functional programming in a functional language. Instead, I'm going to teach you what I learned from functional programming that I use in Java. So this is all about how to think differently in ways that will help you write code in an object-oriented language. I've been writing Java for about 10 years, and 2 years ago, we had a project that my company swore this project was super important for a super important client. And the project was called Pricing Engine, and we spent about 2 months up at the front of this, it was supposed to be 4-month project, writing the UI and iterating through it and showing that to the client. And then finally we got to the meat of the project, the pricing engine itself, whose job was to take all different kinds of inputs and all different kinds of prices and determine how much money the client could expect to make from this contract. And management, who had done the estimate and created the project plan for the pricing engine, had given this portion, the actual engine of the project, 4 weeks. And I looked at that estimate and laughed. But, you know, we dug in and we did our best, and 4 months later, we had something that was functional, that met the requirements we knew about. Thing is, this was 2 years ago. And if I had known then what I know now about functional programming, I would not have laughed at 4 weeks. I would have said, this would be a lot easier in a functional language like Scala. If we have to use Java, maybe I need 6 or 8 weeks. Just knowing how functional programming works would have cut the time for that portion of the project at least in half, probably more. So that's why I'm here today, to tell you what I learned from functional programming and how I tie it back into my Java code. So to start with, let's go back to what we all love about object-oriented programming. Back when OO was new, we thought we would create all these objects and we would line them up and fit together and get beautiful, complicated applications in an elegant architecture. Now and then it actually works that way. But at other times I get a problem that doesn't seem very big, and I apply my best object-oriented design principles to it, and it comes out looking like this. Because object-oriented programming is wonderful, and it has some great applications, but it is not the best paradigm for every single problem. So there are lots of, so functional programming will solve all our problems, right? No. Just like OO, functional has a lot of problems that it is well suited for. It just happens that a lot of the problems that functional is well suited for are problems that are more and more prevalent today. Concurrent programming, lots of parallelism. Web programming works really well with a functional mindset, whether in a functional language or not. So there's lots of programming. And Corey Drew, who's one of my favorite conference attendees, remarks that functional programming is just one paradigm, and any new tool or paradigm you learn will help you in all of your code, including this one. So let's look at the different paradigms. These are just a sampling of a couple different paradigms. And there's one confusion that I want to point out. When I first heard the term functional programming, I said, functional? Well, that's stupid. We've been writing functions forever. Why would we go backwards? But I was thinking about procedural programming. Procedural programming is where we use functions to organize our code, but all we ever do with a function is call it, it returns. We call another one, it returns. The difference between procedural and functional is that in a functional paradigm, we don't just call functions. We pass them around. We return functions from functions. We compose functions, lots of little functions, into slightly bigger functions that do more. So we break things down into a lot of little pieces. That's just a good idea. Composition is a good idea in all cases. So don't get functional confused with procedural. I'm going to talk about 6 principles today. And these are principles. Most of these phrases are mine, but not all of them. So data in, data out, immutability, these are crucial. And we'll talk about all 6 of these. And for each principle, I've got 6 pieces. The name of the principle, what it is, what the purpose of it is, how we already do it, because all of these we use already in some form or other in Java. And then I'll talk about what's the point, why we should do this more. And finally, we'll see examples for most of them in Scala. How many people know about Scala? Half. Good, good, good. So Scala is a functional and object-oriented hybrid language on the JVM. Scala, I get to use Scala in my day job now, which is really exciting. Scala is more object-oriented than Java. So you're not losing any OO switching to Scala or thinking about code in Scala, but it adds the functional paradigm support. And most importantly, we'll see examples of how to use each of these principles in Java. Okay, so first, data in, data out. And I think this is the most important and has had the biggest impact on my code. Data in, data out means that most of your code, most functions or methods, should depend only on their parameters and should do nothing but produce output. Now, if that's all any of our code did, our applications would be very boring, because a data in, data out function always returns the same output for the same input, always. And that, as a whole, would make for a boring program. But it makes for a really testable program. So the goal is to make 80 to 85% of our methods data in, data out, because they're extremely testable. In a test, you have complete control over the input you pass to the function, and you have complete access to the output. So there's no need to set things up in the environment and create data in the database and then take it out in the teardown step. You just create your input, pass it in, get your output back, and do some assertions on it. This is really good. So the goal is to isolate the portions of our program that do need access to the environment or the database, or user input, or need to put something on the screen. We isolate those so that most of our program is data in, data out. It's very testable. And even more important than that, it's easy to understand. Because if you have a function with a meaningful name that describes what it does, and the parameters specify everything that this function needs and exactly what it needs, and the output specifies everything that it gives you back, then you rarely have to go down into the function to find out what it does. And this can give us readable code. The goal of all of my code is to have the main methods, the application logic, read like a lesson in the business domain. We should be able to read what the code is doing, and then the parts that we need to drill down and get more specific, we can, but we don't have to. So how do we do data in, data out? To get more specific, if you have a function that accepts some input and produces some output, but in the meantime, lights flash and something goes up on the screen, that is not data in, data out. If your function accepts some input, produces some output, and also poops out some data to the database, that is not data in, data out. It's affecting the environment. When we are affecting the environment, we want to call that out specifically. Don't hide it 6 levels deep inside a function that says create return output. make your database calls specific, your environment accesses specific. I'm going to give 3 examples of how data in, data out affects my code. One very high level, one a little lower, and one extremely nitpicky. So the good functions, the data in, data out ones, they don't modify their input, they don't access global state, and they don't change anything about the world around them. And if your functions meet these 3 characteristics, I should say, if you have a method in a class that meets these 3 characteristics, make it a static method in some other utility class. Ooh, and that's kind of treasonous, because static methods are not object-oriented. Well, no, they're not, but object-oriented isn't the end-all and be-all. If your function is data in, data out, you can, if it's helpful, put it in a static method, then it's a function, then you have complete access to test it, and please do test it, because if you put it someplace where other people can use it, they will. And this is what makes a good static method. Note that there's a little subtlety, like if your method logs something to the log output, that's technically not data in, data out, because you're affecting the environment. But that's one that I usually compromise on, because now and then logs are useful. But if you are writing a static utility method, be careful with your logging, because you don't want somebody to call it and their logs to get big and fat when they weren't expecting that. So that's a subtle one. All right, backing up, we want to think about the data flow, and I'm going to start from the very high level example. And this is something just a few months ago, when I was working at a startup, we had a task, and the programming task was we've got these deposits and we've got these donations, and we need to match them together and then record to the database which donation was funded by which deposit. And it's quite tricky because not all of them qualify, and we've got to match them in the right order, and the amounts are not the same, and we can match a partial deposit but not a partial donation. There was a lot of business logic. And before I learned about functional programming, I would have solved that problem like this. You come in, you get the deposits, you get the donations, you loop through them, you create the links in the database, you mark them done, you check whether you're finished, and then you loop back to the top. But these arrows, these strings, are tying all the different parts of this little program together. And that has disadvantages. In fact, several years ago, working in retail, I did exactly this when I was matching payments to items purchased. And it was hideous. And I said to myself, I am not doing that again. That was the nastiest code I ever wrote. And at the time, I thought, well, it's just really that complicated. It has to be this messy. But I was wrong. So having learned about functional programming, this is how I wrote on the whiteboard what we should do with those donations and the deposits. At the top is where we're fetching information from the database. At the bottom is where we're putting information in the database, both dependent on the environment. In between is data in, data out. And the data it flows from where we retrieve the deposits and the donation, and it's clear from the diagram, the order doesn't matter on that. But the important part is that matching logic, that's the tricky stuff. That's the important stuff. The matching logic in the middle is data in, data out. So it becomes very testable. And there's something else about this. Once I draw it out like this, I can tell you on each line in this diagram exactly what type of data and more specifics. I could give you more specifics, but I know when I draw this out exactly what should be on either side of that match box. I've specified requirements. And then I draw some circles, and each of these becomes a task. And each of these tasks can be done by a different programmer. In an Agile project, one of the goals is to take one feature and everybody work on it until that one's done. And this lets you divide it up. In the previous architecture, in the old imperative style, one person had to do that because that was all one messy method. But now it's broken up, and it's specified, and it's testable. Especially the tricky part is isolated from any environment access. So I liked this so much that I wrote it up in a blog post. And the blog post was so popular. It was my most popular blog post. And someone translated it into Chinese. So I went to that page and had Google translate it back into English, and this is what I learned. Problem easier, because we know each step of the way of data. That's much better than I could have said it. So when we start thinking about data flowing, that's really where data in, data out becomes really helpful, because we're thinking about the data as moving through the program, and at any point in that process, we can stop it and we can test it, we can check it. All right, so that's the high-level example. Let's zoom way in and get a little bit more realistic and say, whatever, this is some web application, and we want to create an account. Creating an account affects the database. It affects the environment. This method is not data in, data out. However, we've done our best to narrow that down and be as specific as possible when we pass in this user DB service. That has two functions. It gives our method access to the environment, but only a specific portion. So we've been as specific as we can about what this method can do to the environment. Now hopefully, this method does all its database access in itself, but if it calls down into sub-methods, and those methods are going to access the database, it will pass this object to them. And that way, we know, reading through the code, which methods have access to the environment, which ones might poop something out to the database. And that's very useful. So it's not strictly data in, data out, but the environmental access is isolated and explicitly called out. That's the realistic goal. All right, so to get much more narrow focus, methods like this is just a tiny little private method, and these have always bugged me when I've seen them in the code, and at first I didn't know why, but now I do. So here, this class has a couple fields, and it has a private method for validating the password, and it just uses those fields. This is very normal, but this is not data in, data out. As far as that method is concerned, those class fields are global state. If instead we pass in the email and the password, even though that method totally could access the fields, when we do it this way, we're being specific about what the method needs. And that makes it easier when you're reading through the code. You don't need to go into this method to see what criteria it's using to validate the password. I mean, you might if you need to be really specific, but you can see that it uses the password and the email address. And there might be 16 other fields in this class. Data in, data out. It's just more specific. It makes your code easier to understand. All right. Try again. Immutability. I hope I don't have to sell you too much on this. How many of you already try to use immutable classes whenever you can? Good, 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 good. Immutability, we already do it in a lot of ways. But the purpose, this flows really well with your data in, data out functions, because one of those qualifications for data in, data out was that you don't change the input. And if your input is immutable, well, you won't change it because you can't. And we already do this all the time whenever we use strings. Strings are immutable in Java. I like this about them. And Effective Java has like whole sections devoted to how to make your classes immutable. And that's a good thing because immutable classes are wonderful. And changing state in the middle of your program makes it harder to understand. But the bad thing is that it took multiple sections, pages and pages, to explain how to do this in Java. It's hard. In Java, everything is mutable by default. And default mutability is accidental complexity. So we have to fight this. All right. First of all, why do we care? Why would we want to go to the trouble to make our classes immutable? The real reason is because the less state can change, the less we have to think about. It becomes much easier to follow where everything's coming from if it can't change someplace that you didn't expect. The excuse that you give your boss is concurrency, because every immutable class is thread safe by definition. So you don't have to worry about locking, you don't have to worry about deadlocks or things changing out from under you when everything's immutable. But the real reason is because it's easier to think about. For instance, this was last Friday. So I work in Scala, in a functional language, right? And we strive really hard to keep things immutable. But I had to use this library, BioJava, which is written in Java. And I don't know what I'm doing, and the documentation is very poor. So I try some stuff, and I get a null pointer exception. And sure enough, at least I have the source code. I dig it in, and I see that this accession getter returned null. And so I go and I look at that. And sure enough, in one of the superclasses, there's a field called accession. And I'm like, okay, where is this supposed to be set? Public setter, only update. This is supposed to be set anywhere in the world. I have no idea where this is supposed to be set because it's mutable state and it's a public setter, so you might as well have made it a public field for all the encapsulation you're getting. I was very frustrated. So I got a null pointer exception in this case, and it's really hard to figure out what I'm doing wrong because this class is mutable and could change anywhere. Anybody could be changing this state. That's the negative of mutable classes, one of them. All right, so immutability, how do we do it? In Scala, it's trivial. Scala has two ways to declare a value, or an identifier, I should say. Val gives you a value, which is immutable, and that's what you should use almost all the time. And var gives you a variable that can be updated. In our coloring scheme within IntelliJ, any var is red and angry, because watch out. You get used to that immutability, and you start to be able to rely on it, and that's when you really get the paybacks. That's when you realize you don't have to think about a lot of stuff that you have to worry about, because that state can't change out from under you. In Java, okay, the simple stuff is you just make all your fields final and initial them in the constructor. That seems easy enough until you start having objects within your objects, because any object that contains a mutable object is inherently mutable. You may not be able to change the fields directly on your object, but you can get the list out and add to it. Evil, that's why the default mutability is accidental complexity. So how do we deal with that? Well, collections, for instance, we need to make a defensive copy. Anything that we get in the constructor that might be coming in a mutable class, and I say might be, because if you're taking in an interface, just because your interface, like unmodifiable collection, for instance, if you get an unmodifiable collection, well, you can't change it, doesn't mean that implementation doesn't have mutability methods on it that somebody else might call after they pass it to you. So we make a defensive copy. Here I'm using Immutable List, which is part of Guava. Guava is a library created by Google, and it has some beautiful tools in it. Guava gives us just a tiny bit of functional methods in Java. Only going crazy with functional programming in Java gets hideous. Guava gives us just a little bit, and immutable collections are a big part of that. So Guava is really easy to import. I highly recommend it. Immutable list.copyof is a really easy way to create a list that's really immutable. Anybody you pass this list to cannot change it, and neither can you. And then, what happens when you do want to change this class? You want to add a phone number to this customer in this instance. Well, you can't change the list of phone numbers in this customer because customer is immutable. So instead, you have to create a new customer and return that from your setter. That's called copy on modification. And in this case, it's a little complicated because we have an immutable list of phones and we need to return a new customer with additional phones. So I'm using another Guava class here, or static method actually, to construct a new list with all the phones. Okay, so next you say, wow, that's a lot of copying data. That's going to be highly inefficient. But in a functional language, we do this, add an item to the list. We do this all day long. List processing is a lot of what functional languages do all day long. They're the best problems that they solve. But they're not inefficient. They don't reallocate a zillion objects every time they add something to the list. How do they do that? In Scala, or F# or Haskell, or any other functional language, the default list implementation is an immutable linked list. So a linked list has a bunch of elements, and each item in the list contains both the item it's pointing to and a pointer to the next item in the list. And in the case of a functional list, the last item points to the empty list. Okay, that's easy enough. When we want to add to a list, if we add the item to the end of the list, then we have to change what the tiger is pointing to the new item, and then we have to copy the watermelon and have it point to that new tiger, and so on. We have to copy the entire list. That would get really inefficient when you're doing this all day long. But there's an easier way to do it, a little bit thinking differently, and we just add something to the front of the list. And that way, we can put the tomato, we create one new list element with a tomato in it, point it to the front of the banana list, and we're good. We didn't have to copy any of the existing list, none of it. The only object we allocated was the new object we wanted. And it requires thinking a little differently, just getting used to putting things on the front of the list instead of the end, but it's much more efficient. And the reason we can do this is because the list is immutable. Our tomato list can count on the banana, the strawberry, the watermelon, and the tiger never changing because that's immutable. So this is a way that immutability makes immutability more efficient. All right, so in Scala, this is how we would create the new customer. This : thing is called the cons operator for entirely historical reasons. I don't like the word, but it prepends the new phone onto the front of the list. And this is highly efficient, and we're not making a copy of any of the phone numbers already in the list. Okay, so how does that help you in Java? Yeah, I don't know. Guava might be doing this under the covers. But we can extend this kind of thinking to see that copy on mod is not as inefficient as you might at first think it is. Because our customer doesn't only have phone numbers, he has all kinds of other classes. And as long as all these other classes are immutable, we're not going to do any deep copies. We're going to go ahead and create the new customer with a new list of phones, but the same name, address, birthday, and all the cousins we can totally reuse from this class. So immutability is awesome. It's not inefficient, really. People worry about, oh my God, we're creating objects all over the place. We're going to fill up the heap. You know what? The JVM is really, really good at allocating objects and garbage collecting them. And as long as we're careful to reuse the portions of our immutable classes that we can reuse, it's not inefficient. It's really a great idea. And then, from the benefit, you get stuff that's easier to think about. You don't get those null pointer exceptions because if I need an accession, I pass that accession in. It works really well with data in, data out. Oh, it's time for the commercial. Commercial break. This talk is brought to you today by the option type. The purpose of the option: never have a null pointer exception again. Option is a lot like the null object pattern, which is an honorary mention pattern in the Gang of Four, wherein we create an inheritance hierarchy, and you can have either a thing that is a something with functionality, or it is a null thing that does stuff, but you never pass null. And this way, you never get a null pointer exception. Option does all that work for you. have an option of whatever type you like, and you either get some of it or none of it, but you never get no. Scala uses this with the option type. In Guava, it's implemented as optional T, and if you pass this back from your function, somebody is explicitly required to check whether there's something in it, instead of just dereferencing it and null pointer exceptioning. Optional, because null is not a valid object reference. Okay, back to the regularly scheduled program. Verbs are people too. All right, Steve Yegge has a great blog post complaining about how in Java, only nouns have rights. Everything has to be a noun in Java, and if you want to pass a verb into a function, it has to be escorted by a noun. So you can't pass run this, you can only pass a runnable. And it starts to get ridiculous when we wind up passing in the project manager factored creators. We keep wrapping our verbs inside of nouns in Java. And Yegge's complaint was that every verb has to be escorted by a noun, just as in some countries every woman has to be escorted by a man. I'm not okay with this. Verbs need to walk around on their own. So, verbs are people too means functions or values, pass them around. And this is the core principle of functional programming. This is the one that makes a lot of the others possible. So we already do this all over the place. The strategy pattern, the command pattern, the template pattern are all ways for us to supply the how to a class that knows some other surrounding logic. Pass the how into the what, instead of always passing the what. For instance, in a Swing GUI, or most any other GUI, anytime you pass a method, you wrap it in an on-click listener and you pass it to the button, you're passing a verb, you're passing a function. And in Java, that's not pretty, but we still do it all the time. And we should do it more, even though it's not pretty. Passing around instructions is useful, and you don't realize how useful it is until you start doing it more. But in my pricing engine project, this is exactly what I needed, and this is what I would have done differently. So this is what I really did in that pricing engine project 2 years ago. I recognized that I needed functions of all these various inputs because the values change over time, and I needed to calculate totals over the whole of the contract. So I implemented a function in time interface and a whole bunch of classes, because every variable had to be its own class so that it could implement this value at function differently. But in Scala, that would have been prettier. I would have instead had one variable class, and then I would pass in how to calculate it. So in one, I could pass in inflation as a function of time, and we'll just take the power of it. And whereas the seasonal adjustment is actually implemented as an array of very closely specified values over time, and we could pass that in to a different variable without having to create a class for every single one. It would have been cleaner, it would have been faster, it would have been a lot easier to change. But I could have done this in Java. This is how I would do it in Java, and as you can see, it's not pretty. Because out of all this cruft, the only meaningful part of this particular cost inflation implementation is math.pow 1.15 input. That tiny little piece of all this cruft is meaningful. So, in this presentation, we're going to see a lot of cruft. I'm okay with that. I am okay with more lines of code if it means I can divide the code cleanly into application logic and cruft. And what the important part is that the application logic reads cleanly and we can see what we're doing. In Java 8, look at that. It all goes away. The cruft, it's gone. So this is another reason that we should be doing this way more, because once we get Java 8 and we get lambdas, it suddenly gets pretty. It suddenly gets readable. So for now, I tend to just shift the cruft off into a constant or utility class somewhere. And in Java 8, everything will get beautiful. So this is the future of Java. And we can use it now with some effort. All right. One of the things that being able to pass functions does for us is it helps us write in a declarative style. And a declarative style means that we say what we're doing, not how we're doing it. We already do this in a lot of ways. My favorite example is SQL. SQL is a very declarative style. I like SQL because of this. Because we're not telling the database how to get the rows we want. We're not saying, okay, go to this file and retrieve every record and loop through them and see if they meet this condition. No, we're just saying, okay, give me the records that match this condition. It's declarative. Another great example of declarative style is Excel. Excel is entirely declarative. You tell it the dependencies between each cell, but you don't tell it what order to calculate them in. Excel just figures that out. So leave the how out of it whenever you can, and talk about the what. Make what it's doing clear, and if you can, make why it's doing that clear. And the how, let the compiler take care of that. So the point is it makes our code more readable. We tend to get smaller, simpler pieces, little 1 or 2 line methods with a name that states what they do. But the important part is that familiar is not the same as readable. A lot of people at my last job where I was doing Java would look at my code and say, oh, I can't read that. But what they really meant was, that is unfamiliar to me. So Rebecca talked about this morning. She talked about fast and slow thinking. The fast thinking is your gut reaction. The fast thinking is when you just recognize something. It matches a pattern that's already present in your brain. Familiar code, you use fast thinking. You just recognize immediately what it does, and you don't have to think about it at all. Slow thinking is when you actually use your brain and think about what you're reading. Slow thinking is a lot less comfortable. But when I'm writing code, I'm not thinking, okay, I know my other team members and myself, and I know that if I just write it this way, they'll all recognize it, and it'll be easy for them to read. No, I want it to be easy for anybody to read. And fast thinking, familiarity, because it's a pattern match, it depends entirely on your previous perspective. But everybody can do slow thinking with their brains. People don't like to do it sometimes, but everybody can. So that's the kind of readability I'm targeting. If you're thinking about it and you're using your brain, then you can read this, and you might get a lesson in the business domain. This is familiar. Every Java programmer will glance at this loop and know immediately what it's doing. We're clearly pulling out the lines that start with bug from the input list. I hate this code. Whenever I see a for loop, I try to kill it. Try. Some of them, it's just worth it. But this one should die. This is a perfect example of code that's extremely familiar, and Java programmers are comfortable with this because we do it all day long. This is what it should look like. This is a declarative style. This doesn't say how we're getting the items out of the list. This just says we're filtering the list for everything that starts with bug. And in Java, we can do something very similar. This is a Guava method on the iterables class. And we filter the list with a predicate. Predicate is just a function that returns true or false, called starts with bug. And there we've got some cruft. That predicate's not pretty, so I put it in a constant somewhere, and that's okay, because now I don't have a hideous for loop that if it weren't familiar to me, I would have to step through and play compiler and figure out what it's doing. So this is readable, even if it's not familiar. And I had to fight a little bit to get this past the code reviews. But once I taunted them enough about, what, are you afraid to learn something new? Then they calmed down and they used their slow thinking to understand, and then it made perfect sense. So another way that we get a declarative style is from strong typing. I've talked a lot today about you should be able to look at the method call or the method declaration if you're going to use the method and tell exactly what it does. And one ways we get this is by being careful with our types. Strong typing is really huge in Haskell, and it's really a big deal in Scala too. We like to be super specific about our types. Now, what the goal is that we get a red underline instead of a runtime exception. The goal is that we find more errors at compile time and fewer at runtime. Now here's some data that says that in Haskell, which is the strongest type language I know, we find almost all the errors at compile time, and in Perl, it's completely hopeless. I made this data up, but the point is, we're aiming for more errors at compile time. In addition, we get the declarative style. So this is kind of my excuse, really, but the declarative style is more important to me. So we already do this. Rebecca talked a little bit about domain-driven design today. One of the tenets, my favorite tenet of domain-driven design, is to come up with a universal vocabulary. A project should have a glossary, and the same words should be used by the customers, the analysts, the programmers, and the testers. And not just when they're talking about business concepts, but in the code itself. The beginning of wisdom is to call things by their right names. And the more specific we can be, then the more wise we are. So Java is strongly typed, obviously, duh, we use strong typing. We don't even have a choice about that. Yeah, we're lazy. We don't really use strong typing. We use it as much as we're required to. But every time you create a user, for instance, out of a first name that's a string, a last name and a string, and an email address that's a string, lazy. Watch out for that. We think it's strongly typed. Well, it has to be a string. Well, okay, you didn't get an integer, but did you get a first name? What if the caller of your method switches the first name and last name? You're not going to notice. What if your email address has invalid characters in it? You're not going to notice. So we can be a lot more specific about our types than we typically are. That first name is not inherently a string. It's something a lot more specific than a string. It happens to be stored as a string. It's entered by the user as a string, and it's stored in the database as a string. That is not what it is. That is an implementation detail. So if you have a first name, make it a first name. So in Scala, that's easy. You can do it this lazy way and just say, hey, I got a type called first name, and it's a string. You get a lot of the declarative style benefits out of this. Not so much the safety, because any string that you pass in will be converted to a first name. But at least your customer constructor specifies that this parameter is a first name. So you get a little bit more of the specific declarative style, frees you up to name your input whatever you want, because what it is already specified in the type. You can be a little more strict and create a case class in Scala, and this way you have to explicitly convert your string to a first name before you pass it in. Okay. In Java, we can do this. It's just really painful. So you create your first name class. You've got to implement toString and hash code and equals and blah, blah. It's a lot of cruft. Push it off somewhere in a library, and you can still do this. For the record, I do this sparingly in Java, but when it's important, then I really care. And then when you want to create the first name, I like to make a static method that does the construction just to make it as concise as possible. On the other side of strong typing is the interface segregation principle. And I'm not going to get into exactly what this means in Scala because I don't have time, but I will point out this gen iterable parameter. This is a method on list. So if we were writing this in Java, we'd probably assume we're getting a list, but Scala is being as general as possible and saying, I just need anything I can iterate over, and then I can tell you whether it has the same elements as me. In Java, we can do this. So if we're checking whether a customer is valid, but really all we check is the email address, we can be more specific by passing in anything that has an email address. And then we get some more cruft. We get an interface, and we have to implement it in customer. But now our method is more generally useful. So the excuse is, oh, look, my method is useful in more places. But the reason is, my method is very specific about what it requires. This way you know what it's validating without going into the method. Okay. Last principle, lazy evaluation. Dang it. And lazy evaluation means we delay the evaluation of an expression as long as we can. This also would have helped me tremendously in my pricing engine project because I could have used it to not calculate the values of variables that I didn't need. We already do this all the time. Whenever you pass around a provider or a factory, you're delaying the instantiation of the object it creates. SQL cursors are a beautiful example of lazy evaluation because when you get a SQL cursor, when you pass that around, you're not passing around all the data that it could ever retrieve. You're passing around how I'm giving you access to retrieve this data, but we're not actually going to retrieve it until you need it. I like that. Okay, so what's the point? Well, you may never even need it. You may save some evaluations, like I would have in Pricing Engine. That's the excuse that you give your boss. The real reason, one of them, is that you can separate what to do from when to stop. And I'm going to show you what that means. So here's some classic imperative Java that might be familiar to us. And to figure out what this is doing, first, I'll just tell you. So hypothetically, we have some bug in the code, and we need to gather data because it only happens in the production environment, and it's intermittent. So we added a log statement. And this little program reads the log file until it finds the output statement that we added, and then it emails me when it finds one, but only up to 40 because I don't want it to spam me all day long. After 40, I should have enough information. Okay, but I cheated. I told you what it does. Really, as a programmer who came in to modify this code, to find out what it does, you would have to play compiler. You have to step through it and figure out what the computer is going to do as it executes each line, what it's going to change, what's going to be different. If you're reading code and playing compiler, you're doing it wrong. Anybody can play compiler. Real developers work at a more abstract level, a more declarative style. Okay, so in this code, this is the code that reads in the data from the file. This is the code that decides which data is relevant. This is the code that formats it so we can send it in the email. And that's the code that decides when to stop. Bleh. Okay, I'm using Guava here. And there's a bunch of cruft that you don't see. This actually took more lines of code, but here's the important part. We get the data from the file in this code. Here's the code that decides what's relevant. Here's the code that formats it. And here's the code that says when to stop. I'm going to move so everybody can see it. That is a separation of concerns. That is single responsibility. And single responsibility principle is our most important principle as a developer. So I don't care if I had to write that random file iterable, which is the stateful part, and I had to write a predicate in a transform function. That's okay. You can see what this is doing. And this is possible because of lazy evaluation. Because in a Guava iterable, nothing is ever calculated until you need it. So that random file iterable has the capability of retrieving files from lines from a file indefinitely. It'll just keep reading until something's added to the file. And that filter never happens until this as immutable list will trigger the actual processing. And because we have this limit 40 on there, only 40 lines will ever be drawn from the file, be filtered, be transformed. I have 3 minutes. So lazy evaluation of that iterable separated when to stop, and that let us break out these different responsibilities. Okay, that's all the principles. We saw them all. I want to end with Alistair Coburn's oath of non-allegiance. I promise not to exclude from consideration any idea based on its source, but to consider ideas across schools and heritages and paradigms in order to find the ones that best suit the current situation. It's all about which paradigm, which way of thinking solves the problem right in front of you. So I would like to thank Optional for sponsoring this presentation. And don't forget to thank our real sponsors that actually made this presentation possible. And I'm Jessica Kerr. Thank you.
Thank you very much.